Hi everyone, my name is Francesco. I'm from the University of Padova in Italy. I'm a Mercury Fellow there. And today I'm going to talk to you about quantum batteries. Let's see if we can move this on. Yeah, perfect. So basically we're going to talk about energy storage, but we go from a classical picture of metastability to a quantum mechanical one to see if this change of perspective has any consequence on energy storage tasks at a fundamental level. And as you can imagine, the emphasis will be on many body effects and the scaling of the system properties as we increase the number of subsystems involved to see if quantum mechanical effects like entanglement can lead to any advantage for charging, work extraction, and storage tasks. And this is actually the question that started this line of research back in 2013. And interestingly, in 2015, Binder and other authors showed that entanglement is linked, or better, I should say, entanglement generation is linked to a super extensive speedup in the charging of these type of systems. And this observation has since been one of the main driving forces in the field. And it also be the main focus of my talk today. But I also wanted to quickly say that there's been many other interesting discoveries and developments in the field beyond power scalings and quantum advantage, such as results on precision and work fluctuations for this type of settings, stability, so protection from energy leakage from the system to the environment, and also experiments and platforms to test these kind of ideas. So now this is a kind of, it started from quantum information and quantum thermodynamics from a very theoretical setting, but I think now it's become a very interdisciplinary area. And because we are a rather interdisciplinary crowd today, I just wanted to give you an overview of the field to tell you where it started, where we are at right now, and what are the challenges that we face going forward. So first, I'll formally introduce quantum batteries. I'll tell you what they are in a more mathematical sense, and I'll discuss the relationship between power and entanglement. And then I'll tell you about a few proposed ways to achieve these power scalings. A few of them, we've seen them yesterday already. And I'll conclude with an outline of the challenging outlooks that I think are most interesting and most important as we go forward. And so let's start. So what is a quantum battery? So to keep it general, a quantum battery is a quantum system that can store energy and that can develop coherent superposition between its states and also correlations between other subsystems. So this is a very general definition. A more formal one was given by Alinsky and Fannes in 2013 as a quantum system with non-degenerate energy levels, so that you can see the ground state as a dead battery and the excited states as charged ones. And examples, if you like this definition, could be a spin half in a magnetic field. We can have excited electronic states of atoms and molecules, superconducting qubits, cavity modes, but it's definitely not limited to these cases. And for now, we're going to focus on the ideal case of reversible charging or work extraction along the lines of what Felix Binder talked about yesterday, meaning that we'll consider processes that keep the entropy of the system constant during the evolution. And to do that, we'll use unitary dynamics, unitary evolution, which, as you can imagine, generates coherences between the states of the battery. You can think of, for example, of a spin half in its ground states with some applied field to it that makes it oscillate between its ground and excited state. And if the system is perfectly isolated and we turn off this interaction, this charging Hamiltonian, so to say, we'll just stay forever at some excited state. We'll just preserve that energy indefinitely. But in reality, all systems are coupled to their environment and they exchange energy with it. So over time, they will lose energy to their environment. So it's worth mentioning that these would be meaningful energy storage systems only if the relaxation timescale is much slower when compared to the charging and work extraction timescales. So for now, we'll just assume that this is indeed the case and focus just on the charging process. And with all this in mind, we can start having a look at the relation between power and entanglement. To do that, to talk about entanglement, we need to consider many body systems, obviously because entanglement is a type of correlation, a non-classical strong correlation between different subsystems. And just before doing this jump from one to many, I want to give you an example of, let's imagine that we have a 3-level system that is a battery, so to say, in some state. And the state that I presented here, rho, has probability pk of being in some eigenstate epsilon k, with increasing energy. Here, I just chose 1, 0, 1, and 2. And so this system is mostly in its ground state. And in the best case scenario, if we want to charge it unitarily, you will basically swap the probability of being in the ground and excited state. So this is the maximal amount of energy that we can inject into the system. And naturally, not all states can be charged with unitary operations. This state over here, sorry, maybe we should go back. This state over here cannot be charged unitarily because it's already ordered in its energy eigenbase. In principle, it can store more energy, but with unitary operation, it's saturated. Technically, it's called an antipassive state, if we have to use the jargon that Felix used yesterday. But we can just call it like energy saturated state. There's no more energy that we can input into the system with unitary operations. And now we can make this jump. And the very interesting fact here is that we have multiple copies of the same saturated state. That doesn't mean that the collective state is still a saturated state. That's the case only for thermal states. So in general, we have a saturated state, and multiple copies of it can actually accept more energy. We can inject and store more energy into the system. But how can we do so? So there are some unitaries that can achieve that can reorder your probabilities along the energy scale so that we have more energy into the system. But not all unitaries can achieve that. Obviously, local ones, those ones that act only on the individual substates, can't do this because at the individual level, all the systems are already saturated. So we're going to have to use unitaries that are generated by some interaction between the subsystems and that, in other words, are able to generate entanglement between the parties. And so this observation about local and global operation led to the suggestion that maybe entanglement could be necessary for optimal charging and work extraction. And actually, that very year, a group managed to show that entanglement is actually not necessary to perform optimal charging and work extraction. Here, optimal is in the sense of the maximal amount of work that I can input into the system or extract from the system. And this is because we can always keep the system separable at all times just by taking a longer path in the space of states, still using interacting Hamiltonians, so global operations, but by keeping the system separable at all times, by taking a longer path, we can actually achieve optimal charging or work extraction without without generating entanglement in the system. And so the keyword here is longer path. So this was the first hint that entanglement generation might be connected to power rather than the amount of work that is injected or extracted in the system. So we can look at this more explicitly with an example. Let's imagine that we have a register of n spins. They're all in the ground state at the start. And we want to go from their ground state to their excited state. So we want to essentially flip them and inject n units of energy. And there are infinitely many ways to do this unitarily, but we're going to just look at two particular cases. We can consider the optimal local trajectory that is generated by this Hamiltonian here, whereby each spin evolves independently and no entanglement is generated during the dynamics. And we can look at the optimal global trajectory generated by this Hamiltonian over here that generates entanglement between the spins during the evolution. And now, to fairly compare these two options, these two driving procedures, we're going to introduce an energetic constraint, which is on the driving Hamiltonian, not on the internal Hamiltonian of the system. And here, we are just going to say that the amount of energy that we have to drive the system, to charge the system, is at most extensive with the number of components. And the result, if we do the calculation, is that the global Hamiltonian takes it's much faster than the optimal local one. It's actually n times faster. And that translates to a power scaling that is super extensive for the optimal global Hamiltonian with respect to the local one. And it scales like n squared in this particular case with the number of components. So back then in 2017, we called this a quantum advantage as a way to measure the power enhancement that you get from entanglement generation against the scenario where entanglement cannot be generated at all. And we also proved that this quantum advantage, this figure of merit over here, scales at most as n. An interesting thing is that this is also a sort of geometric interpretation to it, which is connected to something called quantum speed limit. And it's basically interpreted as an energy-efficient shortcut through the space of states, with this line over here is a projection of the actual global trajectory on a smaller individual qubit space of states, which is sort of like the best way to utilize that energy from the driving Hamiltonian to charge the system. And I think it's worth mentioning that we have a better understanding, better figure of merit to tell if speed up is quantum mechanical nowadays. And I just wanted to give you an overview of what are the things that you might want to look at if you want to detect the signature of a quantum speed up. So the number one thing to look at is the scaling of the growth of entanglement in the system that you have in the setting of a quantum speed up. And the second thing is a shortcut in energy eigenspace, like I mentioned before. In the protocol that we did before, we just jumped from the ground state to the excited states, but in general, this might be a jump from some low-lying eigenstate to a higher energy eigenstates without populating the intermediate ones. And as you'll see later, there's also collective types of speedups that have no significant entanglement generation and also do not present any direct shortcut between eigenstates in the energy space, but just have a higher speed in the energy space. And that's not to say that super extensive scaling cannot be achieved without entanglement generation. We kind of saw this yesterday implicitly in the talk by Eric. Maybe we'll see that again today. But actually, if we look at this task from this perspective, what we can say is that entanglement is needed if we want to jointly optimize or maximize power and the total amount of work injected. So back then we proved this as a theorem. There's a massive efficiency loss if we want to stay separable while we drive the system at this speed. It can be done, but really you're losing energy efficiency. So to say you're not injecting a lot of work into the system. Okay, so since 2017, there's been a lot of work to find systems that can achieve this power scaling. And the key point is that it's actually quite hard to implement the type of interactions like the one that I was showing you before. And there's been many models that have been proposed, and I'm not going to go into the details of all of them because definitely we don't have enough time, but I just want to give you a quick overview of what the systems that have been proposed are and what we can do with them. So there's been a lot of work on spin chains and spin networks. A lot of work on spin boson models. One of them is the system that James and Eric presented the other day. In this case, the bosons represent more like an energy reservoir, like a charge that provides energy to the spins. We've seen battery charging networks, collisional models, other more exotic ideas. And I think one thing that I want to convey is that the most important resource to obtain a scalable quantum advantage in spin networks is the order of the interaction between the subsystem. So here, if I say k equal to 2, it means that the order of interaction is 2, and that means that I have at most 2 body interactions, which arguably is what happens most frequently in nature. So it was proved last year that any spin networks with k-body interaction can only display an advantage that scales with k, and that is not scalable with the number of parties involved. And so to get a scalable quantum advantage, we need n-body interactions, and these are notoriously hard to obtain. And a system that is promising in this direction is this SYK model. Just quickly, I wanted to say that it's a fermionic model with 4-body interactions that are disordered, that has no classical counterpart, and we can look at this as if it was a spin network by performing Jordan-Wigner transformation. And in this case, we'll see that we have big Pauli strings which correspond to n-body interactions, and we do indeed get a super extensive power scaling that has all the quantum features. So there is a volume low entanglement growth and a sort of shortcut in energy eigenspace, even though it's not as obvious as it was before, from a ground state to kind of like a middle of the ladder. And the interesting thing about this system is that it also has a suppression of work fluctuation, so it's more precise in terms of charging when compared to other many-body systems like many-body localized phase. The There's also another interesting problem, another interesting model is the decay model that was introduced for the case of quantum battery by Dario Ferraro, Gianmarcello, and other authors in 2018. And I think you're going to hear a lot about this model, so I'm not going to focus too much about this, but I just quickly wanted to say that in this case, we also see a super extensive scaling of the charging power, but this doesn't come with the signature of a genuine quantum advantage, meaning that there is not a significant growth of entanglement, and there is no jump in energy eigenspace. There's no direct shortcut or even vague shortcut. And here, I think the good news is that this scaling doesn't rely on entanglement, so that means it's suitable also for like room temperature application where coherences do not need to be preserved between the subsystems. But it also means that this is not maybe the ideal thermodynamic reversible approach to charging that we started from at the beginning. And to conclude with the time that I have left, I just wanted to talk about the challenges and outlooks that we have going forward. And the first most important thing to mention is that a fully operational quantum battery, or however you want to call it, like energy storage system, quantum system, that has a super extensive power scaling has not been demonstrated yet. We've had a few interesting experiments, but either they only did one part of the process, maybe just the charging, or maybe they did the full set of tasks, but only for one subsystem. And I think that's important to realize that this is because there are several challenges for each of these, specific tasks that relate, that change for the different type of platforms that we use when we want to realize these subsystems. So I want to make a distinction between two different separate cases. One is the case of genuine quantum speedups, and the other one is the case of collective speedups. In the case of quantum speedups, these are probably better to be explored on cold platforms, so to say, where we can generate and sustain entanglement between the subsystems, because these type of speedups are definitely based on entanglement. And so maybe it's worth exploring cold atoms, trapped ions, superconducting qubits, and so on and so forth. And for the case of collective speedups, instead, like we said a moment ago for the decay battery model, they're not based on entanglement generation, they're more based on collective behavior, many-body physics. And I guess they're most suitable for this reason for the room temperature application. So in this case, we might look at excited states of semiconducting molecules or MV centers and so on and so forth. Very quickly, just about the cold platforms. At the level of the system, they appear to be the most efficient, precise, and stable. However, they have two major problems. They have a very low absolute energy, and more often than not, in these cases, a lot of energy is already available, so why would you want to store it in the first place? It's a question. The other important thing is that we haven't studied the actual cost of running these devices from the perspective of what Alexia said this morning. So nobody has yet taken into account the effect of cooling and control that we need to run this type of devices. Another really important challenge is, pardon, I think I forgot to mention something. Yes, demonstrating quantum advantage. So I think that for this case, the SYK model is the best and most interesting outlook, but it's also very hard to implement. And in terms of application, there has been a very interesting proposition by Kiribella and others to use quantum batteries as an energy reservoir to perform reversible quantum operations. Super quickly about collective hot platforms. They don't need entanglement. They don't need cooling or coherent control. And another very interesting thing is that if we implement them with, for example, molecular materials, they're characterized by electron volt energy gap, 1 or 2 electron volt energy gap, which is actually quite a lot of energy for such a small system, which might hint that we can interface these type of devices with LEDs, solar cells, and so on and so forth for actually real-world application. But we do face two very important problems if we want to go this direction. At the moment, these type of materials have very low energy density, and this is because as we increase the amount, as we pack more molecules into a system, they start interacting with each other in a rather disordered way if we don't construct an ordered molecular material. And these oftentimes lead to quenching and to a lower density of optical states. So at the end of the day, we kind of lose performance after we reach a certain threshold. The other big problem is the short lifetime of the states that we use in this case. They are about of the order of the nanosecond. If they're optical molecule, they will re-emit the energy they absorbed optically in a nanosecond time scale. So we need to find approaches to extend the storage phase. And there's been a few interesting suggestions. I'll just very quickly go through them. Feedback control and projective measurement aren't very energetically efficient because they need energy to run, even though in principle they work. So I would definitely follow and pursue relaxation-free spaces, dark states, and anomalous relaxations as pathways to metastability, to engineer metastability. So this is it. This is how I would like to wrap it up. The outlooks are the one that I just mentioned before, and we can get further into these details if we want later with some discussion. And another interesting, important thing is to try and understand what could be the application of these devices based on the profiles that we can obtain from different platforms, from different systems. So thank you so much for the attention. I'd like to quickly thank all of you for being here, for having me today, and also my collaborators with whom I recently wrote a colloquium article on quantum batteries where you can find more details about this. Thanks.
Thank you very much. We're actually out of time. Maybe we could just do one quick question while the other speaker prepares. Yeah.
Thank you for the talk. So as a chemist who is working on the traditional lithium-ion batteries in the lab, I'm just wondering what you explained here on the quantum batteries, how much of this is applicable to the batteries we have now? Do we need a big change in them or some modification in the materials?
I think the biggest problem comes from the fact that we chose to call these things batteries in the first place. Back then, it seemed like a very good idea because we were stacking different copies of the same thing, like Volta did back then. But really, we should call them energy storage. They're just another approach to energy storage. So I think it's almost impossible to go from the approach that we have right now for batteries to transition to this type of idea. But we can still leverage on our understanding of metastability, right? Like free energy and how we keep energy stored in a particular system for longer times. Those are things that we can use to sort of get something from the past, so to say, to apply to this new paradigm, especially if we go the direction that James and Eric and others are taking using molecular materials.
Yeah. Thanks. Yeah. Then if we talk about energy storage, it's somehow it could be applicable to that tradition.
Hopefully, yes. I mean, if in the end we're going to store the energy into different stable isomers of a molecule, then we'd go back to chemistry 100%. So at that point, yeah, we'll just have to use that type of approach, yeah.
Thank you.
Yeah.